Hello! In this video we will show you how a new generation of technologies enables system engineers and process analysts to use machine learning to improve and optimize their manufacturing processes. Let's start with the problem. A global semiconductor manufacturer identified a high failure rate during production of one of their chip components. The process engineers would like to understand what may lead to those failures and if they can do something about it. Let's see if the data can help. Here we have detailed readings from 500 sensors monitoring the process. It's a high-frequency stream of data resembling a huge haystack while we are looking for a needle. And here we have quality test results from over 5,000 previous batches. We will bring this data to Xpanse AI project Space and select which outputs we want to analyze. For the initial analysis, we will compare the best batches against the worst ones, and Xpanse AI will look for any possible correlations between the signals in the data and the batch quality. Depending on the chosen settings and the underlying data, this process may take a varied amount of time. In our case, it was under 15 minutes. Most importantly, it's a compute time without the need to manually prepare the data for statistical analysis. After the project execution is finished, we can see a number of sensors with their correlations to the batch quality quantified and visualized. For instance, a brief scan through some of the top correlated factors indicates that certain types of emissions may be correlated with the batch quality. We can also see pressure sensors as being relevant. We can investigate these outputs further by combining additional factors and observing their relationship with the problem. More about that step in a moment. This first pass is only the beginning. As we test different configurations for the analytical objective and experiment with analysis, we broaden our understanding of the potential reasons for defects in the batches. It's an iterative process where the engineering expertise works hand in hand with AI-powered analytics. Questions become clarified and more focused. Irrelevant data is removed and false correlations are filtered out. After several iterations, we end up with a set of the most important levers that engineers can use to improve the process. Let's take a closer look. These charts represent the variance of key process parameters. We can see that for most of the batches, the average temperature measured inside the chamber was typically between 850 and 950. The maximum registered electric current level was typically between 84 and 92, and so on. On the top, we see the number of batches that were produced within those parameters, and also the ratio of failed batches. Our objective is to bring that ratio down. So the big question is, how do those parameters impact the final quality of the manufacturing outputs? We find out exactly how by adding the observed ratio of failed batches on the top of those charts. Now, every chart displays a direct relationship between the process parameter and the quality of the outputs measured after the batch was completed. In the hands of engineers, this dashboard becomes a powerful data interrogation tool, which they can use to optimize their process. For the batches where the max temperature exceeded 950, nearly half of them turned out to be of low quality. Similarly, in a small number of batches where pressure was averaging below 180, over half of them failed the quality test. We'll use the same process to investigate how we can reduce the number of failed batches. For instance, if we ensure that the temperature won't be exceeding 935, we should get an immediate decrease of low-quality batches from 20% to below 19%. By limiting the spikes of electric current levels between 84 and 92, we can bring the failure rate to 15%. Now we can turn to probably the most impactful lever discovered during the analysis: the pressure in the main chamber. It seems that the high pressure is directly correlated with less defects. By keeping the pressure high in conjunction with other changes, it seems we can reduce the failure rate to 5% or perhaps even lower if only the equipment allows it. Some of the findings on the project were confirming the experience and hunches that the engineers had about the manufacturing process. Some others were completely new. The data can only take it so far. It's up to the process engineers to implement experiments and test the findings in real life. Some changes may be more difficult to implement than others. The newly gathered insights may even prompt upgrades to the equipment used in the process. That's all for this video. If you are interested in applying machine learning technology to your data, contact us at info@xpanse.ai. Thanks for watching.